Hey, AP Chemsters, this is Mrs. Valoy bringing you Blankwalle 7.6. This is going to be a really short one because I talked about a lot of this stuff as an intro in 7.5 when I talked about Schrodinger's equation. So we're going to kind of revisit that one more time. I don't know if you noticed this, but I talked about how Schrodinger's equation really explains everything except, beyond hydrogen, because everything we've been doing up until then was hydrogen. And then we reverted back to doing hydrogen again, all right? So we're setting up chapter 8 for electron configuration. And then this is going to include more things besides just hydrogen again, all right? We're not going to do any more math. That equation that we used in 7.5 where the delta E equals -2.18 times 10 to that equation, again, is only for hydrogen. You're never going to be asked, in at least the AP context, to calculate the energies of any other elements besides the hydrogen electrons, okay? So anyway, I'll try to make this quick for you because I know the last one was a little bit long. Again, what's an atomic orbital? I told you what it was in section 7.5. It is the probable location to find the electron in the atom. And again, why do I care about this? Well, because we know bonding is going to come up, all right? And that's where the electrons are. Only the outermost electrons are the one that bonds. Well, we need to know where they are, okay? So anyway, this atomic orbital, though, it's not a perfect sphere. It's not like a ball where it has a definite boundary and, there's air, and then all of a sudden you touch the ball. That's not the case, all right? So there is no sharp boundary where the electrons are never found, that are always found. It's, most of the time, the probable, okay? That's why we're very careful to talk about that. And it's represented by a geometric shape that encompasses the volume where the electron is likely to be found most frequently, typically 90% of the time. So again, we've already talked about this. The s orbital is spherical. The size increases with the the electron shell. There we go, the energy shell. And that's what your N is. That's what we're talking about, N1, N2. N1 is your ground, N2 is the next one, the ones that the electrons are jumping up and out of. All right, so in a sense, maybe this clarifies, if I have an electron on the inside, it'd be your ground level, all right? Then it's going to jump up to the 2 level. Here it is, and this inner ring is going to be N equals 1. It can jump up to N equals 2, N equals 3, okay? So I don't know if you look at these pictures, but the node is the empty space, if you will, represents the 0 probability of finding the electron in that region of space. All right, so the number of nodes was n-1 for the s orbitals. All right, so the S shape again is your sphere. You only have one sphere. But what happens as you go from 1s, so that would be your hydrogen, to your 2s, that'd be your lithium and your beryllium, to your 3s, all right, your nitrogen and magnesium, then what's going on there? So it like encompasses, it's like envelops the electrons from the prior shell, okay? So there is here a region where you will never find the electron, like smack dab in the middle. You'll never find the electron there, okay? And if you look at the picture here, I know mine is colored, yours is not. The darkest red is the highest probability. The pinkish area is the less likely, and the white is you're never going to find them there. So the 1s has the center, you're not going to find it there, but here we call this a node. It's in between the 2 shells, and then there's a node between the 2 and the 3. There's going to be a node between the 3 and the 4, all right? So how many nodes, we don't call this center part a node actually. How many nodes does the S have? The 1s has none. How about your 2s has 1 node, and your 3s has 2 nodes. So again, what are they saying up here? That the number of nodes is n-1. So what about n equals 7? Well, you're going to have 6 nodes, okay? The space is between the shells, okay? The p orbitals, I've already showed you this. Is a plane that slices through the nucleus, divides the region into 2 halves, or 2 lobes, you might hear it. The nodal plane is, again, where the electron is never found, like smack dab in the middle again. So the middle, you're not going to find any, okay? So here are your 3 peanuts, if you will. Your d orbitals has the 2 nodal planes slicing through. So let me go to the next page. So you have, here's a nodal plane and here's a nodal plane, all right? And so you have 5 of these. As far as the nodal planes here, there's 1 here and 1 below. So you have 2 nodal planes there. F's, you have 3 nodal planes. slicing through the nucleus, and you have 8 sections. So here I guess we have 3 dumbbells and 4 shapes. I thought the last picture I found had 8 of the 8 lobes and 1, but whatever. So anyway, predicting the G, I think we can do that. How many orbitals we just said? 9. Very good. General shape, well, we know that we're going to have 8 lobes here, so it'll be 16 lobes. And I guess, I think this would be a quadruple dumbbell. If this is a double dumbbell, as I would call it, you'd probably have a quadruple one for the others, okay? And how does this all work? Why is this important? I really do like the YouTube. I can also post on Google Classroom. And it says a little hokey. The music's kind of fun. All right, you can sing along if you want. But I really do like the visual of how all this works together. Okay, so please go ahead and watch this. We can talk about the final result later. Okay, when we come back together. And that's the end of chapter 7. So it was a quick one, wasn't it? So we'll see you later. Don't wait to be great. Bye, everyone.